Hey guys, we're in phase diagrams in this lab, and let's talk about what a phase diagram is. This is the lecture for it, and phase means basically a mechanical means of separating out different parts. So things that we can see under a microscope, for example, we can establish the UTS, the hardness, the properties of each of those individual unique phases. Equilibrium, huge item here. Time. We want to slow, cool, allow things to change that needs to change back to where they want to go. Diagram means a graphical representation of those phases that are occurring at that slow rate of cooling. Now, you've already had a lab where you've done some grain size measuring, and we have a sample that we can cut. We can put it in a mount, polish and etch it, put some acids, and see things. If we go even further, we can talk about the microstructures in terms of bonds between unit structures here. So if I take steel and I take that steel and I heat it up to a temperature above what we call the recrystallization temperature, which is over 1600 degrees typically Fahrenheit for most steels, and then I slow cool it, I'm going to end up with grains of materials. And this is a good example of those phases. I've got nice white areas here, and those are going to be ferritic or ferrite type structures. This is probably a lower carbon steel, like maybe a 1030 or 1020 type steel. We have some darker regions here, and this one doesn't show up as good on the pictures, but they're kind of fingerprint looking. They're laminar. They're layers and layers of different structures there. And so I can see I have the darker stuff and the whiter stuff, and those are going to be different phases, and I can associate properties to those. Now, when we have a metal and we make it liquid, so we heat it up above the crystallization, we go all to the point that we're liquid, and we start slow cooling it, we're going to have something called a nucleation point, and we're going to see one unit lattice structure of something growing here. And as we cool it down further, those are going to grow and get larger. And so they're repeating blocks, kind of like Legos building on each other. And eventually they start colliding with each other. And where they collide is eventually, as we get it to a non-liquid status and it becomes a solid, we're going to see grain boundaries where these repeating crystals, each individual grain, intersects each other. And so what we have here is a grain of ferrite. This is 100% pure iron, no carbon in it. And when we etched it, the etchant ate out around the grains because that's an amorphous area and it's susceptible to that etchant. And so this is what we're seeing in terms of grains here. Now in steel, we have a structure called body-centered cubic. And this is what happens when we heat a steel up and then we slow cool it. We anneal this material out. It is going to have a repeating structure that's equal on all sides, this cube, that's since the cubic, and we're going to have an iron atom at each lattice point. Okay, now we can put carbon at interstitials right here in between the lattice points. Here we have an atom in the center, and so we can kind of estimate what that unit structure is going to look like. And so as it grows, it gets bigger and bigger. This gives you a three-dimensional understanding of what that grain is looking like. Now then, let's get into what a phase equilibrium diagram is. And the one we're going to start off with is going to be our lead tin alloy. So Pb is lead, Sn is tin. And you're going to be doing this in lab where we're going to cut some lead and put it in a little tray and weigh it by weight. And then by weight, we can cut some tin, and we're going to do three different samples, three different compositions of materials. So we're going to take those materials, we're going to smelt them down, make them a liquid, pour them into a mold, and then we're going to go look at the microstructures and see what phases are present. So looking at this diagram for a lead tin diagram, this line right here that goes up and this way, this right here is what we call the liquidus line. Anything that's above that is going to turn into a liquid. So once we start coming past that line, we're going to see some things coming out of solution. Solution is what we talk about, this liquid, and that this is going to be true because we're talking about eutectic. We'll talk about what eutectic is in another definition later for the steels. This is only good right here for lead tin alloys. we have temperature here. So we're going to heat our stuff up to a temperature that we're going to be liquid, and then we're going to pour our sample and let it cool down. Now, we have some key points here that we want to talk about. This phase right in here is all going to be alpha phase. This is where we primarily see pure lead coming out of solution. Over here we have beta, which is going to be our 10. In here, right here, this is going to be our eutectic composition right here. Anything to the left of that is hypo. Anything to the right of that is hyper. So we hear those terms in terms of blood pressure, hyper, tension, things like that, representing high blood pressure levels. So here's hypo and here's hyper. We're going to talk about the three different compositions from hypo, eutectic, and hyper. Some other notable points that we want to talk about are these numbers right here is 19.2%. That's going to define this point. The 61.9 defines this point for eutectic, and 2.5 defines that point right there. We're going to apply something called the Lever-tie rule, where when we cross this line, this is also known as the eutectic line on this graph, that once we cool down, we come through the liquidus line, we're going to see some stuff come out of solution, and then once we cross this eutectic line, bam, we're into solid down here, and we're going to talk about what we expect to see when we cross that eutectic line. So let's talk about the easiest one to start off with, a laminar eutectic structure. So eutectic structures is basically, look at this purple line going down here. This is the trajectory. We're going to have a composition by weight of about 62% tin, and the rest being lead. We're going to melt it, and we're going to let it cool down slowly. We're going to come through this point. This is our eutectic point, and what we're going to have is 100% laminar looking structures. This is what it would kind of look under the microscope, zoomed in pretty heavily. And this looks like a fingerprint. This is a grain. Here's another grain. This is the grain boundary right here. So you can see the grain boundaries. And those are alternating layers of lead and tin in terms of eutectic formation there. So let's go into tie line hypo. Here we were at eutectic. Now let's look at this trajectory line right here coming down this red line. And again, we're going to go to the liquid status. We're going to cross this line. Some stuff's going to come out of solution. What we're going to see is alpha coming out of solution. We're going to see the lead coming out of solution. So let's talk about this solution, this liquid. It is now becoming rich in tin. So the composition is going to become more and more eutectic-like, to the point when we cross this line, what we're going to see is when we hit this eutectic line here, we're going to end up with so much alpha coming out of solution. Hey, there's our alpha equation right here. And we're going to talk about this tie line here in a minute. And as well, we're going to end up with so much eutectic, kind of the liquid portion, which would be the eutectic here, the laminar structure. And so we have two different equations here. And what does a tie line lever rule? You're going to cover this and how to calculate this and do this in classes. I'm going to give you the short and easy of this. Basically, because this is the lab course, you're going to do a more detailed analysis of this in the lecture courses. But basically, if I put a fulcrum right here, and I wanted to know what percentage of material am I going to get out in one phase or the other, represented by the lengths of these colors here, I can develop an equation. So for the alpha, I can come in here and use these critical points for eutectic and this point right here and write a ratio and calculate how much percent alpha is going to come out of solution. I can look at the rest of the solution and find out how much is going to be eutectic-like by using their data points. And so I can come in here and say by weight, percent 10, put that into these equations, and I'm going to know how much alpha and how much liquid I'm going to have. That's going to be the phases that are going to be representable by microscopic examination here. So if I look at this concept here, and we're looking at a lead tin alloy here. I've got a trajectory really close to the lead, hardly any tin at all. I'm going to see basically alpha coming out of solution when I get down to room temperature. If I have a trajectory that's hypo, that's going to have a composition by lead weight composition, let's say by so much tin here, we're going to come through here. I'm going to see the alpha coming out of solution and the beta being my eutectic. in here. So I'm going to see a little bit of eutectic in a matrix of alpha on here. Now let's talk about our hyper compositions. This is stuff to the right of the eutectic. This is stuff that's going to be rich in tin. Okay, so our tie lever rule is going to change a little bit. If I come down through this red trajectory, I'm going to come across this liquidus line. I'm going to start having stuff coming out of solution here. And what I'm going to see coming out of solution is going to be my beta, my tin coming out of solution. What's going to happen to the liquid? It becomes more eutectic-like. This is my eutectic line. When I cross this, again, I could do a tie lever rule, put my little fulcrum here, and figure out the amounts that are going to be present here. And so what I'm going to be able to do is measure how much percent eutectic I'm going to have by this equation, and how much beta, how much of this phase, 10, I'm going to see in that phase composition. And I'm going to use this equation right here. So again, in the theory class, you're probably going to derive these equations. Here, I'm just giving you the short and easy of here's the equations. Now let's talk about hyper versus hypo on this lead tin alloy and what we expect to see in class. Again, this is for a lead tin system. We talked about the eutectic, starting it off. If I come down through here, I expect to see 100% laminar looking structures here when I polish and etch that. If I'm hypo, I'm on this side of the eutectic line. I'm going to come through here. I'm going to get that alpha coming out of solution. That's going to show up as these spots right here. Okay, that's my alpha, my lead. My liquid is becoming more and more eutectic-like, and that's why I see a matrix of eutectic all around here. Okay, now one of the terms you're going to hear in lab is we're going to say pro-eutectic. This is eutectic. This alpha is pro-eutectic. So if you hear us using that in lecture or in lab, that's one of our metallurgical words that we'll use as a metallurgist. Now then, if I'm hyper, I'm on this side of the eutectic line. I'm high and rich here. I'm going to come into a solidus line or liquidus line here. We're going to start getting some beta coming out of solution. Look at that beta right there. My liquid becomes more and more eutectic-like, crossing the eutectic line, and I'm going to see a matrix of laminar structure with the betas in here. And again, the darkness of this and this depends a lot of how you guys etch these. So we may have to really try and etch lightly and increase our etchant till we can get structures that look somewhat like this, because you're going to have to do phase identification in terms of how much alpha and how much beta and how much of this laminar structure you have on the microscopes to calculate the percentage of weight you have in these samples. Now let's talk about the next phase of this wonderful lab. You guys, we're starting with the eutectic analysis of lead tin alloys. That's great because you got from liquid transformation to solid transformations here. But then we're going to go do still. And still, we're going to go from a solid transformation to a solid transformation. And the diagrams look somewhat similar here. The difference is, for the lead tin, we use the term eutectic alloys. For stills, we're going to use eutectoid because that represents that solid to solid transformation. An iron carbon diagram, this is the full phase diagram for still. The iron carbon diagram is just a small portion of this. Okay, we're just going to look in this zone right here, and we're going to see the percent carbons down here, and we're going to see the different phases that we see in here. We're not going to go to liquid state because all we need to do to heat treat our stills is get up to austenitic structures, austenite, above 850, 800, 900 degrees. Yeah, we're going to get there depending on our compositions, and all these temperatures kind of change based on the actual composition of the metal, the alloys of it. So we get to this austenite, and then we can cool down and we can see what kind of phases we're going to have on it. If we have a lot more carbon in here, then that's going to be considered a cast iron. So austenite, this is our portion in that diagram that was orange. When we heat the still up to the austenitic temperature, and here I'm in Fahrenheit now, 1600 degrees Fahrenheit. You guys need to learn how to work with both. Again, we're above 850 degrees Celsius, 1650 Fahrenheit. We're in the definite austenite gamma range. Okay, so you'll see that sometimes we'll say gamma iron. And basically, this is now changed from a body-centered cubic to a face-centered cubic. It is no longer magnetic here. We have a point where it becomes magnetic, and we call that the Curie point. And in the austenite range, it's FCC, face-centered cubic, and it is non-magnetic. This austenite is going to be fairly weak of a structure, okay? Now we're going to cool it down, and we're going to come through this diagram. This is no longer referenced as the liquidus line. This is now referenced in the textbooks as, over here we have an ACM line, we have an A3 line, we have an A1 line that used to be our eutectic line. We have new names for these, okay? So if you were in lecture, you would want to probably know those names. So we've killed austenite. Here we know what it is. Let's talk about ferrite. If I was to have a trajectory come slowly down this side over here, it is going to end up basically pure iron. So we're looking at percent weight of carbon down here. So pure iron is going to look white ferritic, and it's going to have the grain boundaries on there. Now pearlite is a structure that we need to talk about next. Pearlite is that laminar structure that we talked about that is at a eutectoid composition. No longer eutectic, eutectoid. And we reference this typically as a 0.8% carbon content. It's going to be laminar. And if we look at it, it's a laminar composition of ferrite and cementite, but we just consider this to be pearlite as a whole. And so if I was looking at our microscope, it would look like a bunch of fingerprints laid up, and I can see the grain boundaries here. Again, how we etch it can make it lighter or darker, so that gets to be on you guys about etching it. Error on etching light. If we need to etch it more, you can re-etch it. Otherwise, we'll have to repolish them if you over-etch. Now then, let's look at this. We talked about austenite. We talked about going over here and seeing pure ferrite. And we talked about pearlite, so that's going to do something called the hypoeutectoids. We have another name over here called cementite. Now, cementite is known as iron carbide. We think of iron carbide as being strong and hard. Yeah, this stuff, look at the percent carbon in there. It's very strong. It's got a lot of carbon in it. And so this is something that we really like to see in our stronger steels. Okay, and you notice we put hypoeutectoid and hypereutectoids, referencing this is our eutectoid right here. Now let's talk about our eutectoid, just like we did on the lead tin diagram. And we're only heating up here to austenite. We're not going to go to the liquid phase. We heat up. We're going to have the trajectory line coming through the eutectoid point, and we're going to be solid here. We're going to see 100% fingerprint, laminar looking grain boundaries right here of that laminar structure. And that's pearlitic, okay? So that's what we would expect there. If I look at something that's hypo, that's stuff to the left of the eutectoid, so steels that are going to be less, and what we want to do is this point right here for the eutectic is going to be typically around 0.8% by weight carbon. Now some of the books will say 0.76, 0.2. Let's just use 0.8 for textbook purposes because it's a general number. If I'm dealing with certain alloys, then I would want to define that differently, and there's different thought processes there. Not for this course. So, austenite, we come down this trajectory line. We're going to come across this line, and as we come across, we're going to see stuff coming out of solution. What we're going to see coming out of solution is going to be our alpha. That is going to be our ferrite coming out of solution. So if we're in this zone and we have ferrite coming out of solution, then the solution has to be becoming more eutectoid-like, more pearlitic-like, right? So once we cross this line down here, okay, and we become fully transformed into that phase, we're going to see this composition right here. If I look under a microscope, which is basically right here, I'm going to see these white areas, okay, coming over here, and that is going to be considered our proeutectoid. Remember I talked about that? You'll see that word on some of our stuff. That is basically, you could write down on there that that is our ferrite. So ferrite is proeutectoid. It's not the eutectoid stuff. The stuff that's eutectic looking or eutectoid looking is our pearlitic structure, the layer structures, the dark stuff. That's what we're seeing coming out over here. So we're going to get different ratios of white and dark areas, ferrite and pearlite, based on the percentage of carbon levels that we have. The higher the carbon, the more pearlite we're going to see up to the 1080 composition. Okay, so at 1020 still, we're not going to see a lot of pearlite. At 1060 still, we're going to see a lot of pearlite. All right, and we're going to be doing that on the microscopes and doing phase detection. Oh, this is something I really love. I like to connect the dots, and I don't see textbooks doing this anymore. This is a little bit old school, but this is going to help you understand why we want to talk about phase diagrams. Let's stay on track here with the Hypoeutectoid steels. Remember how we talked about lever tie lines and figuring out the compositions of what's happening for the lead tin alloys? We can do this for these steels as well. And if we look at these diagrams, they have like a 0.76, that's going to be a 0.8 on most of our diagrams. So I can write this nice system here and identify the weights doing a tie lever rule. Again, in the theory class, you're going to learn how to do that and how to generate these equations. Here we're just leveraging these equations. And what it's going to let me do is see how much pearlite came out of solution and what remainder eutectic or eutectoid, the pearlitic structures are going to be. So I can put in my percent weight carbon, so I can put that in there and calculate the percentages I would expect to see under review in the microscope. Now this is what really comes in neat, and I don't see in textbooks anymore. Ferrite has a UTS of 40 KSI. Need to remember that. That is some weak stuff. There's not much into that. Look at the pearlite here. You've got 120 KSI in strength. So more pearlite, I'm going to have a stronger steel. So as the carbon increases, I'm going to have more pearlite in the structure. Thus, it's going to be stronger. Okay. The lower carbon steels, more ferrite, a weaker substance, the steel is going to be weaker. So let's look at a 1020 steel composition wide. I put down the 0.2% into the equations for those, and I can calculate how much ferrite I should see in the microscope. So it should be 75% white ferritic looking structures, grains, and 25% pearlitic looking. That's that laminar eutectoid structure. So that's what I would expect to see in my phase identifications roughly on these two alloys. Now, knowing those two ratios, if I come in here and say 75% is ferrite, I'm getting a net result here of 30 KSI. My pearlite only got 25% of that at 120 KSI. I'm getting 30 KSI here. If I sum this up, my strength for the steel is going to be somewhere in the neighborhood of 60 KSI, and that's pretty spot on for most materials, as a 1020 steel would be. So that's what we like to see about these phases. Remember, phases are identifiable structures by microscope and by strength. UTS, pretty cool stuff. Let's go into the hyper, things that are to the right of the eutectoid. And here we're going to see steels that have above a 1080%. Here it says 76, but again, a 1080 steel would be eutectic or eutectoid, 100%. We're going to see things like a 1090 steel and on having more carbon, and this holds true for it. We got a trajectory line coming down. We're going to heat it up to austenite. We're going to cross this line. We're going to see some stuff coming out of solution, and that's going to be cementite that's going to come out, iron carbide. The solution is going to become more and more eutectoid-like, and then when we cross this line down here, what we're going to see is that iron carbide in a matrix of eutectoid, the pearlite here. And so what I'm seeing, this is what it would kind of look like under a microscope here. I'm going to see some white veins around the grain boundaries. That's where the cementite is going to go. We call this necklacing, and it's going to have these white little areas, and it's very hard to see on some of these. These pictures are a little bit clearer here, and I'm going to see that fingerprint laminar structure of pearlite here. And that's pretty cool that we can see that for the hypereutectoid steels. Now then, just like the hypo, we have the hyper tie line rules here, and we have the UTS for the predominant structures that we see. So we talked about that we're going to see pearlite in there, and we're going to see cementite. Look at the UTS. Now remember, UTS of ferrite was only 40 KSI. Perlite was 120 KSI. Cementite is a 350 KSI. This stuff is strong. That's because it's iron carbide. Now, we can calculate doing the tie lever rule directly right off here. They're leveraging the compositions off the phase diagram. In short, we're giving you the quick, easy of it. Put my percent weight of carbon in here. I can calculate for like a 1090 steel here how much perlite I'm going to have. 98.2% for 1090 steel. 1090 steel is like a spring steel. It's heat treatable. It's got enough carbon that we could heat treat this. I teach a lot of knife making, and that's the first steel we actually make, a 1090 steel, because it's easy to heat treat, make, grind, and it's a great steel for learning on. Then we go to cementite down here. We only got 1.8% cementite. Not much of that. Again, applying the UTS to the percentages we have, the perlite is giving us like 117 KSI here, where that strong cementite, because we don't have very much, is not really giving us anything net here. We sum these up, we've got about 124 KSI. Yeah, it's a lot stronger, almost twice as strong as the 1020 steel, because we have more carbon in there in the form of the structures that we want to have go on there. Now, that's pretty much the gist of this lecture. You're going to see a video on using the equipment for the lecture, and I hope this helped.